Alright, this is my submission for homework 1, where we're going to be running linear and nonlinear regressions on the Antoine equation based on experimental data to figure out the arbitrary constants A, B, and C. And without further ado, let's get started with the nonlinear regression. First thing we want to do is open X. No, I'm just kidding. I'm kidding. Let's get to the real stuff. Okay. Well, it looks like I didn't clear what I meant to clear, but as you can see, the very first thing that you want to do is get the .csv file from GitHub. And what that involves is a shell command called wget, and then the link. Remember, you want the raw link from GitHub, so this is what you immediately see when you pull up the CSV file. You want to hit raw and get that URL right there and run it. Well, evaluate it. And it evaluates correctly, all that nice stuff. And we can get started with evaluating the rest of the code. So, first thing we want to do is to import your necessary packages. The first of which being numpy, so import numpy as np. And we also want to use a package from SciPy called optimize minimize. So from scipy.optimize, typo, import minimize. Okay. And finally, we want to be able to plot things, and we're going to use plotly for that. So from plotly.subplots import make underscore subplots. Okay, and we're wanting subplots because we want to be able to put more than one data set on a single plot. Oh, that's the explanation anyway. And just because we want it to be in dark mode, let's go ahead and import plotly.io as po and run the command po dot templates. I think that's the correct one. Po dot templates dot default equals plotly underscore dark, and everything evaluated correctly. So we're smooth sailing for now. Okay, with importing the packages out of the way, first thing we want to do is take that CSV file and put it into a numpy array. Quick reminder on what a CSV file is. It's essentially a text file of comma separated values. That's what the CSV stands for. So we want to use a numpy command. Well, first we want to call the object data. Okay, and we're going to use np.read. Oh no, not read. Load? Yes, load txt. And the first argument that load txt takes in is the file name, which is water vapor pressure.csv. And you can just copy that, paste it, boom. The second argument we want to use is define a delimiter. Okay, and a quick reminder on what a delimiter is. It's any character that will be able to split up that long string in the file into individual elements in an array. With this case is a comma, because comma separated values. Let's evaluate it. It runs correctly. Fantastic. Next thing we want to do is to, actually before we do that, let's make sure that we are seeing what we want to see, which is this. Excuse me. The left column is temperature in Celsius, and the right column is pressure in pascals. And we want to put those into two different arrays, T and P. Okay? So, get rid of that. T, we want to equal to data, right? All values in row 0. Remember that in Python, arrays index starting from 0, not like MATLAB. And P, pressure, is equal to data in the second column. I apologize. Column, not row. And let's double check that. T, it's there, what we want to see. And P is also what we want to see. Okay. I'm going to, okay. The next thing we want to do is plot our data to see what it looks like. And a quick reminder on what our equation looks like. It's the Antoine equation is log base 10 of P is equal to A minus B over C plus T, right? Now, what we really want is to see what the value on the left side hand of the equation is. So let's define that into an array where log 10p, actually let's make that lowercase, log 10p is equal to np dot log base 10 of p. And you'll see why we want this value instead of p later on. And that's what we're going to plot on our y-axis. So let's make a figure object. Fig equals make underscore subplots. Is that the correct syntax? Yes, it's the correct syntax. And then fig dot add underscore scatter x equals t, y equals log 10p. Mode markers, because we want a scatter plot. And name, we'll name this data. Ooh, doesn't like the syntax. What does it not like? Markers. I'm missing an S. Mode equals markers. And look at that. It's a logarithmically growing function. Okay. Now we know that our data is there, and it's set up the way that we want to. Let's move on to doing the nonlinear regression. And what the nonlinear regression really does is it's going to take a look at each of these data values and calculate how far away is each data value from the ideal line of best fit. And we're also going to use the scipy function to minimize that error. What that error is formally called is the sum of square sum error. So define the function. We need a sum squared error function that takes in a vector of unknowns, where those three unknowns are our three arbitrary constants, a, b, and c, and unpack that from the vector that's taking in. And what we want to return is, we're going to build this equation together, all right? We want to return the square of the difference between the experimental, which is our log 10p, and our model, which is this equation. So let's start with just that equation. Okay, so our log 10p minus our model, a minus b over c plus, oh, let's add a parentheses there, plus t. Okay. And what this is essentially doing is checking the height. What's the difference between each data point and the ideal line of best fit? Okay? But we're getting negative and positive values. And we don't want that, because we want to eventually sum all of that together and have an absolute value. We don't care if it's negative or positive. We just care how far away it is from the line of best fit. The way we get rid of that, square the whole thing. Okay? Oh, I forget. Python does not like carets. In order to do exponents, that's 2 asterisks. Okay? Remember that. And np.sum to sum all of that into one big value. It's okay. All right. We have our error function. Next, we want to use the minimize function from scipy in order to minimize the error function and get it as small as possible in order to find what our arbitrary constants a, b, and c are. So let's start with minimize. And the first argument that it takes in is going to be your error function. A function, it takes in any function, but for our purposes, we're putting in our error function. The second argument is going to be a vector of the guesses of what our 3 arbitrary constants are. Now, ideally, you want to get that as close as possible to the true constants, or the true minimum, right? Well, we don't know that, but we can make an educated guess. We know that it's the constants for the Antoine equation of water vapor. And we know that the A is going to be around the magnitude of 1 or 2 digits, so we'll choose 1. We can play around with the values later, but maybe it works on the first try, we'll see. The second value, b, we know is something on the order of magnitude of 4 digits, so arbitrarily, let's put down 10. And again, c will be around the magnitude of 1 or 2 digits, we'll put in 0. And let's run it, and it doesn't overflow, which is good, and it says success is true, which is also good. And finally, the array that it spits out is our 3 constants, A, B, and C, right? And we look at it, and it's what we want to see. It's what we would expect from the Antoine equation for water. But to really make sure, let's plot this against our line of best fit. Or, sorry, let's plot this against our data. So, let's unpack this vector, A, B, and C. Alright, now, this function, what it's really spitting out is this whole string here. We don't want that. We just want x, the array of 10, 17, 56, and negative 36. So the way we do that and tell Python that we only want x is add a dot x at the very end. And there, it evaluates, it's happy, and we're good. Now, let's bring this plot down past the our nonlinear regression code. And the way you do that is, I think it's Control M, Control K. Oh, that goes up. Control M, Control J, Control M, Control J. Look at that. It's at the, one more. Control M, Control J. There we go. It's at the bottom. Well, let's add our plot against this. And the first thing you want to do is, we want a array going from around 300 to, 650. And we want linearly spaced coordinates, because right now, if we use our t to plot it, we have big straight lines, and it's not going to look great. Regardless, let's call this t plot, otherwise temperature for the purposes of plotting, equals np dot linspace. Now remember, linspace is the numpy function that creates linearly spaced array from start to stop, and we can tell it how many we want in between. And like I mentioned, we want 300 to 650, and let's say something like 150 points in between. Doesn't really matter, okay? Let's add our model, which is fig add scatter. X is equal to our t plot, temperature for plotting purposes. Y is equal to our equation, and I wrote it before, so why don't we just copy that, bring it down, paste. Majesty of computers, right? And remember, t is not t. T is t plot. T temperature for plotting purposes. And our mode we want to be line. And name we'll call it non-linear. We don't need underscore. Non-linear Antoine. And I think that's good. Let's evaluate it. And look at that. Good fitting line for our nonlinear regression. I'll be right back, and we will meet on my iPad to then explain how to do a linear regression. All right? Okay.